Good day, everyone. This is the Chapter 5, Making Networks Work. This chapter spans the entirely theoretical to the profoundly practical aspects of networking. Here, you'll learn about two different but complementary theoretical models for what networks are and how they work. First, you explore the Open System Interconnection or OSI reference model for networking, which explain how networks behave within an orderly, 7-layered model for network communication. Then you'll learn about the IEEE 802 networking model and the standard that surround the 802 designation. OSI and 802 networking models. The concept of networking is almost as important as the real thing. Several proposed models seek to create an intellectual framework within which to clarify network concepts and activities. Of all these models, none has been successful as the Open System Interconnection or OSI reference model proposed by International Organization for Standardization or ISO. The ISO is a network of national standard institutes from 140 countries. The expanded name differs from language to language. This chapter also describes the IEEE 802 networking model, sometimes perceived as an enhancement to the OSI model and sometimes as a family of specification for networks of many kinds. This is one of the most influential sets of networking standard in use anywhere. Rule of a reference model. You might wonder why a reference model for networking is needed in general, and why the layer concept in particular is so valuable. To illustrate the value of the layers, consider the process of purchasing mobile telephone service. All the functionality of each option and feature involved in mobile phone service can be broken into layers. At the most basic level of layer, there is the type of communication, such as analog or digital. OSI reference model. During the latter half of 1970s, the ISO began to formulate a theoretical model for networks of all kinds. In the late 1970s, the organization drafted what became known as the Open System Interconnection or OSI reference model. It is interesting to note that ISO formulated its standards deliberately to avoid proprietary vendor requirements. Although the grand vision of OSI was never realized, it did bring debate about open system to the forefront. Like the reference model, this consciousness is also as an enduring legacy of the OSI effort. One word, layers, conveys the essence of the OSI reference model. Essentially, this model's foundation rests on the idea that networking can be broken into a series of related tasks, each of which can be conceptualized as a single aspect or rather a layer of the communication process. Understanding layers. We discussed layers of the networking process and presented a simulation that depicted a chat session. Layering helps clarify process of networking, groups related tasks and requirements. The OSI reference model for networking makes explicit many communication activities and related tasks and requirements. This frame of reference clarifies what networks are and how they work. For the letter delivery, several activities, for example, placing the letter in the envelope and addressing and sorting the letter, happen well before the delivery of the letter. OSI reference model structure. Simply put, the OSI reference model breaks network communication into 7 layers: application, presentation, session, transport, network, data link, and physical. Uppermost in the reference model, the application layer provides a set of interfaces that permit network applications, such as Windows Explorer, an email package, or a web browser to access network services. Those applications reside above the reference model and communicate with its top layer. At the bottom of the reference model, the physical layer is where the network medium and the signals that traverse it reside. All the activities necessary to handle network communications occur between the top and the bottom layers. Protocol stacks provide a software that enables computers to communicate across a network. Currently, the most common protocol stacks include the following. First, Transmission Control Protocol Internet Protocol, or TCP or IP. The protocol suite used on the Internet, which is also the default protocol for Windows 2000 to 2003 Server, Windows XP, and Novell NetWare 5 and later. Next is Internetwork Packet Exchange or Sequence Packet Exchange, or IPX or SPX. The protocol suite most commonly used with NetWare version 4.by and below. NetWare 5.by and above use TCP or IP as the default protocol. And the third is NetBIOS Enhanced User Interface or NetBEO, a protocol suite developed by IBM for PC networking and traditionally used in IBM and Windows products such as Windows NT, Windows 9X, and Windows for Workgroups. And the fourth is AppleTalk, the protocol suite developed by Apple for its Macintosh computer and still commonly used in Macintosh-based network. And the last one is System Network Architecture or SNA, the protocol suite developed by IBM for use with its mainframe computers. These protocol stacks combine with drivers for whatever network devices are attached to a computer, provide the crucial software link that permits application to communicate with a network. Each individual layer in the OSI model has its own set of well-defined functions, and the functions of each layer communicate and interact with the layers immediately above and below it. In general, the purpose of any layer in the model is to provide services to the adjacent higher layer but also to shield that higher layer from the details of how its services are implemented. In the reference model, layer construction follows an abstract concept called peer layers. That is, each layer on one computer behaves as if it were communicating with its twin on the other computer. This is sometimes called logical or virtual communication between peer layers, as shown in figure. On its way down the stack, before data gets passed from one layer to the next, it is broken down into data units, sometimes called packets or payloads. The official OSI acronym is PDU, sometimes interpreted as Protocol Data Unit, or Packet Data Unit, or even Payload Data Unit. The PDU is a unit of information passed as a self-contained data structure from one layer to another on its way up to down the stack. Application layer, also called Layer 7, is the top layer of the reference model. It provides a set interfaces for applications to obtain access to network services as well as access to the network services that support applications directly, including services such as network files transfer, message handling, and database query processing. The application layer also handles general network access, the movement of data from sender to receiver, and error recovery for applications, where applicable. The PDU at this layer, as well as in the presentation and session layers, is referred to simply as data. Examples of software that resides at this layer include File Transfer Protocol Programs or FTP, Hypertext Transfer Protocol or HTTP, and components of client software such as the client for Microsoft Network or the Unix or Linux NFS client. Possible problems that occur at this layer include missing or misconfigured client or server software and incompatible or obsolete commands being used to communicate between a client and the server. Next is presentation layer. The presentation layer or layer 6 handles data format information for network communications. For outgoing messages, it converts data into a generic format that can survive the rigors of network transmission. For incoming messages, it converts data from its generic network representation into a format that makes sense to the receiving application. The presentation layer also handles protocol conversion, data encryption or decryption, character set issue, and graphic commands. A special software facility known as a redirector operates at this layer. The redirector intercepts requests for service from the computer. Requests that cannot be satisfied locally are redirected across the network to whichever network resource can handle the request. Software components that operate at this layer are usually built into the application layer component. These include FTP clients and servers, HTTP clients and servers, and client for Microsoft Network. The presentation layer deals with the details of data presentation. An example of functionality at this level is a web browser displaying graphic files embedded in a web page. In such a situation, the presentation layer component informs the application layer what type of data or graphic format to display. Session layer or layer 5 permits two parties to hold ongoing communications, called a session, across a network. This means application on either end of the session can exchange data for as long as the session lasts. The session layer handles session setup, data or message exchanges, and turned down when the session ends. It also monitors session identification so only designated parties can participate, and monitors security services to control access to session information, or to permit only authorized parties to establish sessions. Some of the common network functions handled by this layer include name lookup and user login and logout. Thus, the domain name system, or DNS, and NetBIOS name resolution both work in part at this layer, as does the login and logout function built into most client software, such as FTP, Client for Microsoft Networks, and NFS. The session layer also manages the mechanics inherent in any going conversation, including identifying which side may transmit data when and for how long, and maintaining a connection through transmission of so-called keep-alive messages designed to keep inactive from shutting down an open connection. Transport layer or layer 4 manages the conveyance of data from sender to receiver across a network. It segments arbitrarily long data payloads into chunks that match the maximum packet size for the networking medium in use, includes error checks to ensure error-free delivery, and handles resequencing of chunks into the original data on receipt. The transport layer also handles flow control. Flow control ensures that the recipient of transmitted data is not overwhelmed with more data than it can handle. The PDU at this layer is called a segment. The components that work at this layer include the TCP portion of the TCP or IP protocol suite and the SPX portion of the IPX or SPX protocol suite. Problems that occur at this layer include a corrupt or bug-ridden protocol stack and segment that are too large for the medium in use on a network between the source and destination networks. Next is network layer. Network layer or layer 3 handles addressing messages for delivery but also translate logical network addresses into their physical counterparts, which are known as the MAC address. The network layer also decides how to route transmission from sender to receiver. To determine how to get from point A to point B, the network layer considers factors based on network conditions, quality of service information, cost of alternate routes, and delivery properties. This layer is also traffic cop for network activity and handles packet switching, data routing, and congestion control. When moving data from one kind of network medium to another, the network layer also handles fragmentation and reassembly function based on disparities between dissimilar media. This means the network layer downsizes packet coming from a medium that handles larger PDUs to a medium that handles smaller packets. This process is called fragmentation. When the data arrives at the receiving end, its final destination, the network layer reassembles the downsized pieces into their original packets. The network layer is the first layer in which we can discuss the operation of the networking device. Routers operate at this layer, and now some advanced switches that have built-in routing functions can also operate at this layer. Data link layer. Data link layer or layer 2 sends PDUs from the network layer to the physical layer. The PDU at the data link is called the data frame or frame. On the receiving side, layer 2 packages the raw data from the physical layer into data frames for delivery to the network layer. A data frame is the basic unit for network traffic on the wire as sent across the medium in more general terms. Its highly structured format within which payload data from upper layers is placed for sending and from which payload data from upper layers is taken on receipt. Figure shows the contents of typical data frame. Notice that it includes IDs for both sender and receiver as well as control information and the data integrity check in addition to its data payload. Control information covers a multitude of topics from identifying specific frames types to providing routing and segmentation data. The payload is the information that originated from an application, segmented and labeled for network delivery. The data integrity check, called a cycle redundancy check or CRC, is a special mathematical function based on the bit patterns in the frame, sent as part of the frame itself. The CRC is recalculated on the receiving end. If the recalculated and sent values agree, the assumption is that the data was received in the same form it was sent. Physical layer is a layer 1. Its job is to convert bytes into signals for outgoing messages and signals into bytes for incoming ones. In other words, the physical layer orchestrates the transmission of whatever form a data frame's bytes take when dispatched across the network medium. In the capacity, the physical layer manages the computer's interface to the network medium and instructs the driver software and the network interface what to send across the medium. It also translates and screens incoming data for the delivery to the receiving computer. Physical layer handles the intricacies of transmitting the pattern of bytes that represent a data frame from the sending to the receiving computer, even though those bytes are arbitrary at this layer, and the digital format may not even represent them. IEEE 802 Networking Specification. By the late 1970s, it was clear that local area networks or LANs would take an important place in business computing environments. Spurred by this realization, the Institute of Electrical and Electronic Engineers or IEEE launched an effort to define a set of LAN standards to ensure the network interfaces and cabling from multiple manufacturers would be compatible as long as they adhered to the same IEEE specification. This effort was called Project 802 to indicate the year 1980 and month February of its inception. Since then, the IEEE 802 specification have taken firm root in the networking world. Project 802 concentrates its effort on standards that describe the physical elements of a network, including network adapters, cables, connectors, signaling technologies, media, access control or MACs, and the like. Most of these reside in the lower two layers of the OSI model and the physical or data link layers. In particular, the 802 specification documents describe how NICs may access and transfer data across a variety of networking media. They also describe what's involved in attaching, managing, and detaching such devices in a network environment. IEEE 802 specifications. IEEE codified the various efforts undertaken as part of Project 802 in a number of standards categories, numbered 802.1 through 802.20 as shown in the table. Standards 802.1 through 802.5 are the greatest interest, with the some attention devoted to 802.11, 802.12, 802.15, and 802.16. These categories are the focus of ongoing development and extension effort at the IEEE through its working groups. These categories also the repository of a large body of extending standards. IEEE 802 extensions to the OSI reference model. The two lowest layers of the OSI reference model, the physical and data link layers, define how computers attach to specific networking media and how such computers can access those media without impeding one another from communicating across the media. The IEEE 802 specification expanded the OSI reference model at the physical and data link layers, which define how more than one computer can access the network without causing interference with other computers on the network. In the figure shows how the 802 standards provide more detail at these layers by breaking the data link layer into the following sublayers. The second is Media Access Control or MAC sublayer. Provide shared access for multiple NICs with the physical layer. The MAC directly communicate with a computer's NIC and it's responsible for ensuring error-free data transmission between computer on a network. The data link address born into every NIC's PROM is called MAC layer address because it operates at this sublayer of the 802.2 specification. Figure shows the IEEE 802 specification map to the LLC and MAC sublayers to provide specification for LLC, CSMA or CD networking, token bus networking, token ring networking, and demand priority. And that's all for the chapter 5.